Look at some properties of limits. And we're going to look at some things that some of them are just really painfully obvious, to the place where sometimes students stumble on them because they're so obvious. Okay? Here's the first one, the limit of a constant. If capital A is a constant, then for any real number C, the limit as x approaches C of A is A. What they're saying there is that if you have, oh, I forgot I wasn't on that. If you have a constant function, so let's say these are your axes, like y equals 3. Y equals 3 looks like this, right? Does it matter what x value you're going towards? No. Any x value you go towards, the function will go towards 3. All right? So what about the identity function? When they say the identity function, do you know what that is? It's y equals x. Y is identical to x. That's going to go through things like 2, 2 and -5, -5, right? So for any real number, and this is one where occasionally students are like, can it really be this easy? The limit as x approaches C of x, well, they just told you that x was approaching C, right? It's got to be C. Okay, again, some of these are pretty self-evident. The next one isn't as self-evident. The limit of a sum or a difference or a product. So if f and g are functions for which the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, it can't be that one of them's infinite or does not exist or something like that, then if we take the limit of the sum of those two functions, it's the sum of the two limits. If we take the limit of the difference of the two functions, it's the difference of the two limits. And if we're taking the limit of the product of those two functions, we can simply find those two limits separately and then multiply them together. And we're good to go on any of those. Notice what's conspicuously absent at this point. Yeah, division's absent. We're going to talk about that, I think, in a minute. So if, for example, we're taking the limit as x approaches 1 of 2x times the quantity x plus 4, although no one after a day is going to take the time to write it this way, this is the limit as x approaches 1 of 2x times the limit as x approaches 1 of x plus 4. As x approaches 1, what does 2x approach? 2. And as x approaches 1, what does x plus 4 approach? 5. So that's 10. I'm certainly not going to require that you show as part of your work that you have split this up this way. So for most cases, we'll simply do something like this. As x goes to 2 from the right, well, what does 4x approach? 8. And what does 2 minus x approach? 0, and 8 times 0 is 0. Any questions about that? All right. By the way, I threw on the from the right. just to see if it would shake your confidence in that. It doesn't matter that it's approaching from the right, it's approaching 0. Now, later on, there will be some where when we approach 0, it is important whether we approach from the left or the right, but we'll get to that in a little bit later. So, since f of x raised to the nth power is the product of n f of x's, we have the following extension of the limit of a product. If the limit as x approaches c of f of x exists, and n is any positive integer, then notice it has to be a positive integer. If it is something else, we may not be able to do this. Then the limit as x approaches c of the quantity f of x raised to the nth power is the limit as x approaches c of f of x, then raise it to the nth power. So if we're trying to find the limit as x approaches 8 of 2x minus 11, well, as x approaches 8, 2x approaches 16, minus 11 is 5, so that's just 5 to the third, which is 125. So, to speed up the work, so you don't have to ever show any of that, we note that for any polynomial p of x, where p of x is a sub n, that's some constant, times x raised to the nth power, plus a sub n minus 1, that's some other constant, times x to the n minus 1, etc., 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 is simply a combination of those previous rules. So the limit as x goes to c of p of x is just p of c. Remember I said we don't care what happens at c, but sometimes we'll use what happens at c to get the limit. With polynomials, we can always just use what happens at c to tell us what happens as we approach c. It's the same thing. And it's because, and we'll talk more about this later, oh, that's interesting. It's because a polynomial is a continuous function. And again, we'll talk more about continuity later. So if, for example, we're just doing the limit as x approaches 3 of 4x squared minus x plus 2, that's a polynomial, so all I have to do is substitute in let's see, that's 4 times 9 is 36, minus 3 is 33, plus 2 is 35. For this next one, since we have a piecewise function and we're looking for the limit as x approaches 2, and that's where the two pieces, start and stop, we need to look at the limit from the left and the limit from the right. So the limit as x approaches 2 from the left of f of x is going to be the limit as x approaches 2 from the left of which one of these two expressions talks about things to the left of 2? Yeah, the 3x plus 1. So that's just going to be 3 times 2 plus 1 is 7. On the other hand, the limit as x approaches 2 from the right of f of x is governed by this equation. So that'll be the limit as x approaches 2 from the right of 2x times x minus 1. Let's see, that's going to be 4 times 1 is 4. So what do we say about the limit as x approaches 2 of f of x? Yep, it does not exist. when the left-hand limit and the right-hand limit don't agree, then the limit does not exist at that point.
If we show like all that work, do we have to do like the because blah blah blah?
No. By showing, I guess maybe we should show that these aren't equal to each other, but you've showed that they're not equal, even if you haven't written it. If you want to be really complete, it's probably better if you write those both on the same line and put a big not equal to in between them. Okay? It's a good question. What if it's a fractional power? Remember the rule we just used, it had to be an integer power, which took care of all of our polynomials. Polynomials always have integer powers on our variables. And they're always positive integers. So if the limit as x approaches c of f of x exists, and f of x to the m over n power is defined for integers m and n, then the limit as x approaches c of f of x to the m over n power is simply the limit as x approaches c of f of x raised to the m over n power. So basically what happens is this has to be defined. Let me show you what I mean. So for this, what power are we using here? The 1/3 power. Thank you, Sam. So it's the limit as x approaches 4 of x squared plus 11 to the 1/3 power. That should be equal to the limit as x approaches 4 of, let's see, that'll be 16 plus 11 is 27. Is 27 to the 1/3 defined? Yeah, it's 3. It's the cube root of 27. When would that not be defined? Can you think of a case where it wouldn't be defined? What kind of an expression? What? Yeah. So like if we ended up with negative 16 to the 1/2 power, well, that's not defined. So that limit is not going to exist. You just say the limit does not exist. Usually on these, they don't ask you to explain why. They just ask you, what is the limit? So let's take a look at this one. This is just going to be 9 to the 3/2 power. I included this one mostly because sometimes students forget what that means. What does it mean to be raised to the 3/2 power? Yes. Although I always do it the other way. It's the square root, then raised to the 3rd power. It doesn't matter what order you do them in, but I don't know what 9 cubed is easily off the top of my head. But I know what the square root of 9 is, and I know what that number is cubed. I always cut it down first and then, but you're right, it can be either way. So I always think about that as the square root of 9 cubed. So that'll be 3 to the 3rd, which is 27. All right. As I pointed out earlier, quotients were sadly missing. And it's because we have to be careful with quotients. So if the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, and there's the additional part. the limit as x approaches c of g of x isn't 0, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. So those limits have to exist, and the denominator can't be 0, because the one thing in all of math, when you were a little kid, they told you in some elementary class at some point, you can't take 5 from 3. Lies. Yes, you can. Or at some point someone said, you can't take the square root of a negative number. Lies. You can take the square root of a negative number. It's just an imaginary number. You have to have a different type of number. But in all of math, if you try to actually divide by 0, it's always, nope, can't do that. Okay, that one never changes. Well, at least not in my experience in math. There may be some higher math that I haven't studied. But so for these, what we're going to do is simply go, okay, well, that's the limit as x approaches 1 of 3x cubed minus 2x plus 1 over the limit as x approaches 1 of 4x squared plus 5. So that's just 2/9. And frankly, I will, after today, I'm never writing that again. Okay? Now, you do want to do them independently of one another, and we'll get more into that another day, but there are times when this doesn't work out real well. So, if we're looking at this one, what does my numerator go to as x goes to negative 2? 0. And what does my denominator go to as x goes to negative 2? 11. So that's 0. Oh, by the way, it's not really a secret, but on the AP exam, this would most likely be a multiple choice question. It would not be a free response question. But if it were a free response question, you can leave your answer like that, because it is a numeric answer and it's equivalent to the final answer. On free response questions on the AP exam for calculus, you never have to simplify numeric answers. So if you had, this will come up where we'll have 3 plus 7 plus 8 plus 12. Stop writing. Just leave it like that. Because the only thing that can happen, this answer is, let's say this answer is correct, right? Can I make it more correct? No. You have the opportunity to make a mistake, right? And sometimes lose a point that you'd already gained. Okay? So when we get to doing things like that, you don't ever have to simplify your numeric answers.
What about, say the square root of 25?
You could leave it that way.
Leave it that way?
Yep. That's a numeric answer. Pardon?
As long as there's no x's or y's.
Yeah, it has to be numeric. There is kind of a question about trig functions and stuff. Can you leave it as like the sine of pi over 3? And the answer is usually it's okay, but not always, which drives me crazy. But we'll get to that later. All right. Let's look at these two. And I'm going to cheat because I'm already looking ahead on both of these, and I know that badness is going to happen, and we're going to have to do something a little different. I am going to evaluate the numerator and denominator separately here. So if I take the limit as x goes to -2 of x squared plus 5x plus 6, let's see, that's going to be 4 minus 10 is -6 plus 6 is 0. I'm okay with the numerator being 0. But for the denominator, when I substitute into that polynomial, I also get 0. 0 over 0 is called an indeterminate form. Which means you have no idea what the number is. It could be anything. And the reason why is we actually have 3 mathematical rules competing. The first one is 0 over a number is usually what? 0. And a number over 0 is usually undefined. And a number over itself is usually who wins? So when you get an indeterminate form, that means you got to do more work. You can't just say, oh, it's an indeterminate form, I don't know what it is. What we're going to do is this. I'm going to rewrite this as the limit as x approaches -2 of, and I'm going to factor both the numerator and the denominator. How does the numerator factor? Right? X plus 3, x plus 2. And what about the denominator? X plus 2, x minus 2. Now, x plus 2 over x plus 2 is equal to 1. Everywhere except at x is -2, right? But when we're doing a limit, do we care what happens at that point? No. So we can actually drop these. Now, the numerator goes to 1, the denominator goes to -4, and the answer is -1/4. So again, the only reason we can drop those is because this is a limit. This function is not equal to this function. Right, with these crossed out, because this is undefined at -2, and once I've crossed those out, this is defined at -2. All right. So that's going to come up on your homework tonight. If you get an indeterminate form, one of the ways that you can deal with it is to factor and see if something cancels. If it does, great. If it doesn't, well, then you probably shouldn't have 0 over 0. Okay? Now, let's take a look at this one. I'm actually going to show you 2 different ways to do this one. If, let's just real quickly in our heads do the evaluation. This would be the square root of 5 minus the square root of 5, which is 0, over 5 minus 5, which is 0. I have an indeterminate form. I've got to do something to it. There are 2 different ways you can approach this problem. I'm going to show you what most textbooks show, and then I'm going to show you there is a way to do it without doing that. But you have to, it's a little bit different okay? Here's what most textbooks show you to do. When you have something like this, what we're going to do is we're going to multiply both the numerator and the denominator times the square root of x plus the square root of 5. This is called the conjugate, right? Have y'all ever heard that term in math before? Okay. When you were doing complex numbers, when did you do complex numbers? Did you do them Algebra 2 or last year? Algebra 2? So if you have 3 plus 2i and 3 minus 2i, those are called complex conjugates. It's the same terms, but instead of plus you have minus, or instead of minus you have plus. Something cool happens when you do this. I'm going to multiply the denominator also by the square root of x plus the square root of 5. Does everyone agree that I've multiplied by 1? Which shouldn't change anything, right? But it is going to change how this looks. So, in the numerator, I'm going to keep my limit. I can't stop writing the limit until I've evaluated it. The square root of x times the square root of x is x. Now that's not quite true, but it's close enough. You have to be careful. If x is negative, this is undefined. But since we're approaching 5, we're okay. So that's going to be x. And then I'm going to have square root of x times the square root of 5 is the square root of 5x, and I'm going to have a positive one of those. And then I'm going to have a negative one of those. Oh, that's nice. And then I'm going to have negative square root of 5 times positive square root of 5 is negative 5. Over, I'm not going to distribute the denominator. And you're like, why not? Well, this is one of those hang on and you'll see in just a second. So now simplifying the numerator, I get x minus 5 over x minus 5 times the square root of x plus the square root of 5. What do you see that I can do now to simplify this? Yeah, let's not say scratch out. Let's say divide out. Now, is this equivalent to the original expression anymore? No. But it is equivalent to the original expression everywhere except at x equals 5, which is why we can do this. So now we get 1 over the square root of 5 plus the square root of 5 is 1 over 2 square roots of 5. That's one way to do this. It works really well. I'm going to show you another way, but you have to think about it a little bit differently. So remember back to those carefree days of Algebra 1 where you learned to factor things like that? And what does this factor to? Yeah, x plus 5, x minus 5. And it was because the rule was if you had x squared minus something else squared, you could do that, right? You can do that on this problem. You can actually factor x minus 5 using square roots. Let me show you. We're going to have the limit as x approaches 5 of, my numerator is, I'm going to leave alone, square root of x minus the square root of 5. Would you agree that my denominator is the square root of x squared minus the square root of 5 squared? It's kind of weird to think about that, though, isn't it? It's not the normal way you think about factoring things, but it is. So I could rewrite that as the limit as x approaches 5 of the square root of x minus the square root of 5 over the square root of x plus the square root of 5 times the square root of x minus the square root of 5. The two square root of x minus 5s I can divide out, and I end up with 1 over 2 square roots of 5. I kind of like the second one better. Although it is a weird way to think about factoring something. And actually, when we factor, we usually try to factor a polynomial into other polynomials. So we've taken something that was a polynomial and broken it into things that aren't polynomials anymore. That's why it feels so strange. Because you've always done from a higher powered polynomials to lower powered polynomials multiplied together. Did I lose anybody on that, or you guys are all okay? Okay. All right, I have a worksheet for you for your assignment this weekend.